spring seminar. We are very happy to have Nico from Utrecht, and he'll tell us about elastic Eikonal amplitudes near the black hole. Over to you, Nico.
Thank you. Do you see this? Oh, right. Okay, that should be fine.
Yes, I can see your pointer. Yeah.
All right. Yes, thank you for the invitation. This afternoon I will talk about elastic Eikonal amplitudes near the black hole. And this talk will be based on research done over the past couple of years in collaboration with NAVA, who's also at the ICTS, my supervisor here at Hooft, and Fabiano Filippa, who was a previous master student at the UU and is now doing his PhD in Salerno. Okay, so the original drive for our research was a pure interest question out of quantum gravity. Namely, what can we learn from a field theoretic model of gravitational perturbations around a black hole? So normally, or well, not normally, but most of the time when people do field theory close to the horizon, it's a field theory in curved spacetime where there's some ingoing and outgoing modes, but these don't have any interaction. And we wanted to ask the question, what happens when we add interaction between these modes, specifically interaction by a gravitational perturbation? So classically speaking, perturbation theory has a large amount of applications in general relativity due to the widely available different scales. There are different masses, length scales, time scales, and a lot of dimensionless parameters can be constructed to do perturbations around. And in particular, there are many nice applications to binary systems where two objects spiral around each other. So a familiar pedagogical example is the asymptotic wave emission. If you can find using a perturbed field H that can be expressed in terms of some bulk stress energy tensor, and then we have an asymptotic H. And this can also be used to express this in terms of a multiple expansion, giving some multiple behavior for the gravitational wave emission. And more precise methods have also been done for the in-spiral in the case of in specific scenarios. So if they're both of a roughly equal mass, the in-spiral dynamics, how they get closer to each other, can be modeled quite nicely using a perturbation around the flat background. However, if one of them is much smaller than the other, the mass ratio becomes very small. And in this case, one needs perturbation around the Schwarzschild of the bigger mass, where the smaller one exerts a cell force. So in recent years have also been field theoretic schemes developed that can use these gravitational perturbations within field theory to achieve important results with respect to what's also on the last slide. So in particular, the post-Minkowskian expansion, which is an expansion of a weak gravitational field around a flat space-time in a fully relativistic manner. This PM expansion can be used to describe classical observables by using on-shell scattering diagrams. So these would be the kind of diagrams here where there are external scalars or other massive objects, and they exchange some perturbed graviton to exchange information. And this method can in particular be used to predict the scattering angle, waveform, and power emission of binary and spirals, which is a huge success. However, this PM expansion fails in the case where one of the masses is much smaller than the other. So for extreme mass ratio in spirals or EMRIs. In this case, classically speaking, one needs to do perturbation around the Schwarzschild of the larger mass. And then the smaller mass will follow approximately a geodesic in the Schwarzschild spacetime. However, because the smaller mass has its own gravitational field, this gravitational field interacts with the background, generating a cell force. And the cell force field is exactly the perturbation. And on a flat background, it obeys this equation. So it obeys the wave equation on a curved spacetime. And so this means that the cell force field radiates away towards infinity in terms of gravitational waves. So there's interest in finding this exact cell force because we can possibly measure that gravitational wave signal. And heuristically speaking, we expect that this kind of radiation we can extract using radiative or dissipative diagrams, where there's one at least one external graviton emitted. So this is a possible future prospect. And so for the general aim of our research, we'll be considering perturbation, H, small perturbation around the Schwarzschild background. And we will try to construct a field theory with this to do calculations. So the Hooft has shown semi-classically that using this perturbation, the following S matrix must be true between the in modes and out modes of the black hole. And our first question was whether we can reproduce this result in field theory to make sure that we understand both of the models. So we have formulated the field theoretic model of the black hole perturbation. And first, we want to reproduce the Hooft's S matrix. That is what this talk will be about mainly. And some next steps will be to try and use this model to understand the nature of the near horizon. So in particular, we can calculate soft theorems using the soft emission diagrams. And we can try and use the near horizon theory to find near horizon symmetries that are likely similar to BMS because the horizon is a null surface. And we can hopefully relate the soft theorems to the symmetries. And finally, as mentioned, we can possibly model EMRIs using the radiative diagrams. So during this talk, we will focus on completely understanding the elastic interactions that we can construct in the theory. And in particular, we will solve gaps between the Hooft's original S matrix and our intermediate field theoretic results that in the end had to be promoted to something more general. And to do so, we will calculate the most general Eikonal interaction possible, which is an Eikonal interaction between arbitrarily many particles. Then hopefully we can do the inelastic interactions in the near future. So for the talk outline, we will have two parts. And first, I will review what has already been done. So we will review the derivation of the Hooft semiclassical S matrix. Then I will show the field theory surrounding the graviton that we have developed to do calculations with, and the initial Eikonal results, which we call the minimal coupling. And in part two, we will resolve the issues that came surrounding the minimal coupling by resumming over all of the partial waves, because the minimal coupling we have made an approximation as spherical harmonics. And in the end, we will generalize this to arbitrary many particles. So first, we'll briefly review Hooft's quantum mechanical S matrix. This is based on his 1996 paper. So some definitions to clear this up. We'll work on the Schwarzschild background in Kruskal coordinates, where the light cone component just has the function A of R that's given by this. The coordinates are defined in a slightly different convention to have some easier numerical constants in the end. So there's a numerical rescaling. And in here, the inverse Schwarzschild radius mu has been defined, being 1 over R, because we'll see that this mu will keep coming back as an effective mass parameter. So it's useful to define it separately. And then the system that the Hooft considers is that we have a Schwarzschild background where there are some particles going out of the black hole and some particles going into it. And the main question is, what is the relation between this in and out, these in and out states? And the S matrix proposal states that these must be related, the out and in, exactly by this S matrix. And this S matrix can be derived using any interacting theory. So the Hooft's observation as to how to derive this S matrix was that the energy of particles, as they get closer and closer to the horizon, this energy will diverge because the energy on the Schwarzschild background goes as the asymptotic energy divided by this Schwarzschild scaling factor. So close to the horizon, this diverges. And so his proposal was, well, if the energy diverges, the gravitational field will be extremely strong in some sense. So we have to include gravitational interaction because this will, this will give the fundamental leading contribution. So in his setup, we will consider highly energetic in particles because they will be close to the horizon. And then these in particles generate a shock wave on top of the Schwarzschild background. So the metric is given by the Schwarzschild background, but there's an additional component which gives a shock wave where the in particle will be extremely close to the horizon. So it's close to the U equals 0 hypersurface. And there it generates a singular metric where the function, the prefactor f of omega, can be found by plugging the metric into Einstein's equations. So you have a differential equation with on the right-hand side the stress energy tensor of the in particles. And the effect of this shock wave on the out particles is that it generates a shift in their position that is proportional exactly to this prefactor in the metric. So graphically, we can visualize this as follows. So the blue line is the highly energetic in particle, and the red line is some out particle. And as soon as this out particle hits this line, this hypersurface of the in particle, its position gets shifted by this amount, and from there it continues to move on its own path again. So effectively, all out particles are dragged a bit along with the in particle. And this shockwave effect can then be used to derive his quantum mechanical S matrix. So we will define some
I,
distribution.
I have,
Yes.
yeah. So this infalling shell that you have that you indicate with the blue line,
Yes.
this is part of your geometry. This is not a dynamical thing that like this is not a part of your S matrix, is it?
Sorry?
So the infalling shell, the blue line,
Yes.
is part of your background geometry, or trying to understand why the infalling shell doesn't get displaced or translated due to this collision. There's a collision, right? It's like particle collision. So why doesn't the infalling shell get displaced due to the interaction or collision?
So you mean why the interacting, why the blue in particle doesn't get displaced also by the red particle? Why they don't have some more complex interaction?
Yes.
Yeah, so that's a very good question, and this was also something that was confusing me. So Hoof's argument was that, well, you're close to either of the horizons, so the in particle will always be much, much, much heavier than the out one if you're not close to the bifurcation point. So then this kind of interaction will be leading, and close to the bifurcation point, we need a theory of quantum gravity to understand the interaction. And this was a heuristic way of reasoning around it that did not satisfy me personally, which is also one of the reasons why we wanted to develop this field theory, where the particles just have an arbitrary interaction, which goes either ways, so that we resolve this.
So I should think of this thing as being suppressed by Planck mass or by the energy of the infalling shell. What's the parameter which controls this suppression?
So the reason for the shift being dominant only on one of the two, I would say that the parameter responsible is the ratio of their energies. If this ratio is roughly equal, then of course they should shift each other. But if one is much heavier or more energetic, then this would dominate.
I see. Okay, thanks. And this large energy in your mathematics shows up at was what? So I'd like to follow this in your talk. So yeah.
This one? Right.
I see. Is this E infinity is the energy of the infalling shell, is it?
Yeah. The infinity means the asymptotic energy when you're extremely far from the black hole. That's the.
Sure. And you said it's very large because of it getting blue shifted as we come close to the horizon, is it?
Yes. Yeah, because then you approach this small r becoming capital R.
But okay, and could you go to your Penrose diagram once again?
This one?
Yeah, but doesn't this collision also happen near horizon? Why shouldn't I think of the red particle also as getting blue shifted? Is it because it's coming from inside? Yeah, this a bit confusing. It looks like it's coming out of the white hole, right? The red particle.
Yes, it's coming out of the white hole indeed. This is the only way to model the outer particles on the internal background. Yeah, that's a good question, and I think it has to do with the fact that this equation talks about the actual energy with respect to time, which I have only written down as a motivation. But what we actually need are the light cone momenta, and the way the light cone momenta shifts, they shift differently because this depends on which of the horizons you're close to. And because this light cone momentum is orthogonal to the horizon, I think it doesn't shift when it's close. That's what I can recall right now.
And why do you say this is the only way to model? I mean, why couldn't the red particle come, from outside the white hole? Why does it need, it could come from some other spherical angle, right? From spatial infinity.
From here, you mean?
Oh, it's a null particle. That's why.
Yes. Yeah.
Yes. Okay. Fine. Thanks.
Right. Okay. Yes.
Yeah.
I see what you mean. Yeah, it's a null particle. Yeah. Thank you.
Thanks.
So yeah, we have this function f of omega that's related to the stress energy tensor by this differential equation. And now we can express the stress energy tensor in terms of distributions of the in particle. So there are a whole bunch of in particles, and they will define some distribution with a sum over each of their momenta and the angle at which they're inserted into the black hole. And then its Hoof's S matrix was found to be given by this complex exponent. So as usual gravitational coupling, there's an integral over both of the in and out particles, distributions, and there's a Green's function that relates the two. And the Green's function is exactly the Green's function of this differential operator that we saw before. So this gives the Hoof's S matrix in the position basis. But because the differential equation depends on the spherical Laplacian, it makes sense to do this in spherical harmonics. So this is another possible formulation that the Hooft only came to more recently, where we can expand the distributions in partial waves. And then the S matrix diagonalizes, and this Green's function becomes just 1 over L squared plus L plus 1. So yeah, we've seen the S matrix as it was derived by Hooft. There are two possible formulations. One is in partial waves, where we have diagonalization, and the other is in position space, where we have the full integral, the Green's function. And now our desire was to reproduce this in field theory. So now I will show you the field theory that we've developed, which is based on this paper. So as already mentioned, we will be considering a linear graviton field H that is a perturbation around the Schwarzschild background in the same convention for the Hooft. And for the scalar part, for the mass part, we will just consider a massive scalar field for simplicity. Then the full action of this system is given by this. So we have a quadratic action of the perturbation H that couples to the linearized Einstein tensor. Then we have a coupling between the H and the stress energy tensor, which is in turn given by the scalar field, and the scalar field's own quadratic action, which is the usual Planck-Gordon action. And now from this, we want to find the propagates and vertices. But this action is far too large and complex to be able to just do that. So we first, similar to Hooft's latest insights, moved to spherical harmonics in order to simplify off the equations. So the scalar in spherical harmonics is as usual, but the graviton, when we expand it in spherical harmonics, will consist of an even parity mode and an odd parity mode. And we'll fix the gauge of it to be the radiative gauge. And then these even modes will have along the light cone a light cone tensor capital H. So the small a and b are the light cone indices. The coupling will vanish, and the capital AB, the two-sphere component, will be proportional to a light cone scalar k. Whereas on the odd parity side, the light cone and the two-sphere component vanish, but only the coupling is non-zero. and has a light cone vector, HA in it. And all of the rest of the contributions come from the spherical harmonics in the sphere. So what we find when inserting this whole expansion into the quadratic actions is that the odd and even modes decouple naturally. And this is because of the spherical symmetry of the background. So the odd modes will only come into play in the vertex, and we'll look at that at the next slide. And I want to mention that for the special case where L is small, if it's 1 or 0, then the gauge condition isn't sufficient. So we have an additional condition that the light cone K and the H is traceless and the K vanishes. And for L equals 0, there's even another condition, which is that the vector also vanishes. And in the paper, we treat these cases separately all the time. During the talk, we won't do this because of the time. So the coupling vertex of the odd modes, it couples still to the scalars. And this coupling is proportional to the angular momentum. So the light cone H couples to the angular derivative of the scalar. And in order to simplify the system, we will assume that this angular momentum is small. It will be of the order of this effective mass. And we'll see later why this is a reasonable this effective mass is a reasonable order of magnitude, which we assume to be much smaller than the center of mass energy. And this comes again from the heuristic reasoning that the center of mass energy will become very large close to the horizon, but the angular momentum is conserved throughout. And so we can take this limit where we neglect the angular momentum. And in this case, this vertex is subleading compared to the vertices that come from the light cone momenta only. And so we will neglect the odd modes altogether and focus only on the even modes. And doing this whole spherical harmonic expansion, we can integrate the two-sphere out, and then symbolically we arrive at the following action, where there's no more integration of the two-sphere, only of the light cone, and everything depends on Ln, and there's a residual r squared from the two-sphere Jacobian. And most importantly, the metric has also become two-dimensional, which is now conformally flat. So nice next simplification is to well transform the metric, the field, to make it actually two-dimensional flat, and to also transform the fields to remove the residual r squared. And inserting this entire well transformation gives this kind of action. So still a symbolic notation, but the important part is that the integration is over a flat two-dimensional space, and we have partial derivatives, and some potentials that depend on R and that are in general very complex. So as a final approximation, we want to do field theory in the end in momentum space. So we approximate this near the horizon, because that's where we expect the scattering to be dominant. And then when doing this approximation, we can finally use a Fourier transformation to write the action in the following way. So they're the quadratic actions, which are still quite large, but the important part is the vertex. So there are all of the usual integrations, but what we see is that the scalars couple to a very specific combination of the gravitons. So it makes sense to rescale our graviton to change the parameterization of the graviton modes to be this precise quantity that couples in the vertex, because then we simplify our vertex tremendously. So we subtract the trace and this scalar k. And then finally, we arrive at the following action. So we just have the residual mode h that we defined in the previous slide with some inverse propagator. There's the Klein-Gordon action of the scalar field with a 4D mass, but now also an effective two-dimensional mass that comes from integrating out the two-sphere. And there's the vertex, where there's just this one graviton mode that now couples to the scalars. So the vertex is, in a combinatorial sense, extremely easy. And the remaining graviton modes, those don't couple to the scalar, so we could integrate them out of the path integral. And now finally, we can read off the Feynman rules. So the scalar propagator is just the usual Klein-Gordon propagator with the dual masses. And the graviton propagator, we know by this capital P, which consists of two parts, a soft part that only depends on the matrix, and this effective mass parameter mu squared and lambda, where lambda is L squared plus L plus 1, and the hard part that depends on the graviton momentum that we will see drops out of the calculation in the end. And I want to remark that the hard part vanishes exactly for L equals 0 and 1. So these were the special cases and observations that only this remains. Then the vertex is given by the coupling between two scalars and the graviton. And we have it's proportional to the scalar momenta, the gravitational coupling, and this effective mass mu. And there is the integral over 3 harmonics still remaining because this doesn't diagonalize, so we cannot simplify this any further. And so now we want to use this set of Feynman rules to derive the S matrix and compare it to the Hoofts. But the problem was that the vertex is very complicated. Namely, it mixes the different LMs, whereas we knew that the Hooft's S matrix diagonalizes in the LMs. So in our initial calculation, we forcefully diagonalized the vertex in order to find the diagonalized S matrix. This is what we did in this paper, which we call the minimal coupling. So the setup in the scattering is as follows. We have one external particle that comes from asymptotic infinity, that is at some finite LM, and one that is coming out of the black hole, that is interpreted as some kind of spherically symmetric vacuum contribution of the black hole, and so being at L equals 0. I want to say that this picture is, we have improved on it, but I want to go through this section to show the timeline of how we did things. So we have this one external particle going into the black hole and going out. They have some kind of gravitational interaction given by the diagrams. And then the ingoing particle continues its way, now being also at L equals 0, whereas the outgoing continues outwards, being at the same LM, because this must be a conserved angular conservation. Then in order to calculate this interaction, we define the minimal coupling vertex. So it's still two scalars in the H, but effectively we will always choose one of the scalar fields, the dashed line, to be at L equals 0. And it being at L equals 0 means that spherical harmonic becomes constant, so that the integral just becomes over 2, and this diagonalizes, which is what we desired at the time. However, we didn't manage to find a corresponding physical limit that could give this. There's no parameter that we can scale or make small. There's no symmetry that gives this. So it turned out in the end that we needed to improve to generalize the result. But this is initially the way we did the calculation. So using this vertex, we can calculate the sum of an infinite amount of ladder diagrams, which is the Eikonal resummation. So the ladder diagrams are the diagrams where the two scalars always stay either on top or on the bottom, but they can exchange an arbitrary amount of gravitons in between, and these gravitons can be permuted in either way. So at one loop, there are two options, which is either parallel or crossed. At two loop, we have these possibilities. There are 6 diagrams. And at 3 loop, there will be 24, and this grows very quickly. Then the combinatorics of this whole problem has been done by Levy and Sugar, and we can in 1969, and we can use the way that they did the calculation to write down our S matrix in the minimal coupling, and it's given by this. So the one is if the S matrix it would find in the free field theory, where there's no gravitational interaction. And so the S matrix is effectively given by a complex exponent with the gravitational coupling, the momenta, and this L squared plus L plus 1 factor. And when we now compare this to the one that the Hooft has found, we find that it's remarkably similar. It's almost equal. There's some numerical constant that mismatches, but we fixed this later at some point. This was an issue of interpretation. But more importantly, the G, the momenta, and the L squared plus L plus 1 agree exactly. So this was a very satisfying result. And we felt like this minimal coupling system works. However, when we want to remove the LMs, because it Hooft has this quantum mechanical formulation where there is also a formulation in terms of positions. When we wanted to do that on our review theory side, this turned out to be impossible because the minimal coupling removed all sense of position and LM. So we knew that we had to improve. So to summarize the minimal coupling result, we found that there was a good match between the field theory result and the quantum mechanical result in partial waves. However, the position space was impossible to match, and in field theory, we just didn't have any starting point. And also the foundation of this minimal coupling is actually very unclear. It appears that mathematically there's no way to argue why this would be allowed. So in the end, it turns out that we needed to resum over all of the partial waves in the vertex. And that's what I want to talk about in the second half. So are there any other questions or issues so far? Okay, then we continue to the resummation. So the first step was to, first I investigated what this resummation does on the tree level to see how this changes our system. So for the vertex, we will now consider the full vertex where the prefactor remains the same, but we have this integral over all harmonics. That means that every propagator in the diagram will be at a different LM. And we must sum over this LM each time. And every vertex will contain another integral over the angles. So the expressions will grow quite quickly. So in our tree level, we have a 2-to-2 system where we can analyze the kinematics. So there are 4 particles now, but all of these particles may be at a different L because we removed the minimal coupling. And that means that effectively they will all have some different mass. 4D mass is the same, but they have a different effective mass from the 2 sphere. And for these external particles, we can define the usual momentum exchange, P1 minus P3. And from this, we can define the Mandelstam variables T and S, where T gives a measure of the exchange and S the center of mass energy in the system. And as mentioned, we will be working in the limit where S is very large. So one remarkable thing that we found in 2 dimensions is that the momentum exchange Q can be fixed exactly in terms of the Mandelstam S and the masses by using the on-shell conditions and momentum conservation. And there turn out to be 2 solutions. One is the Q minus, where the momentum is exchanged all the way from top to bottom. And so the corresponding T minus is also a very large number, absolutely speaking. So this will be a case where there's a lot of momentum being transferred. The other solution, the Q plus, has these factors that are proportional to mu squared over S. So these are extremely small. And the Q plus solution tells us that there is some momentum exchange, but only a tiny amount to ensure that all of the external particles remain on their mass shell. So only the masses are exchanged. And for the rest, they keep their dominant momentum contributions the same. And the corresponding T plus we can see also as proportional to mu squared over S. But this is the smallest momentum exchange contribution. And so what we find is that the plus solution is the smallest, and this will be the leading contribution in the Eikonal. This can be quickly analyzed at tree level, and it's much harder for the loops. We will assume this T plus to be leading. And then we can calculate the following diagram. So all of the external particles are different LMs. There's a graviton exchange that adds some other capital LM. And this capital LM must be summed over, and we have an integral for each 2 of the vertices. So in the large S limit, we find this expression for the tree level amplitude. There are the 2 integrals, there's a factor similar to the minimal coupling, and there are the 6 harmonics coming out of the vertex. And in order to understand this this diagram a bit better, we can observe that 4 of the 6 harmonics depend only on the external LNM. So it makes sense to define these separately. So we define all of the external ones in terms of some YIV, some initial value harmonic. And then the amplitude can be written down much more compactly with the gravitational coupling, the S squared double integral of the YIV, and the F of omega and omega bar, which is given by this summation of the 1 over lambda of the graviton and its remaining two harmonics. And upon inspection, this function f is exactly the Green's function of the Hooft, defined by this differential equation. So this Green's function emerges naturally when we resum the partial waves, which is a very nice result from the resummation. And now we can move to the question that we couldn't answer in the minimal coupling, namely what if the external fields are not partial waves, but they are at certain angles. So we can do this by resumming the creation or annihilation operators with their respective spherical harmonics. And doing this summation over the spherical harmonics together with the YIV turns them into a delta function, removing the integrals. So what we find is that the amplitude becomes just the prefactor times this Green's function between the positions of the two particles that go into the scattering. So this is a very different result from the minimal coupling, where we just had the prefactor with a slightly different numerical constant. So there's a crucial addition, which is a distance-dependent factor for the particles that we couldn't obtain before. So this partial wave resummation clearly gave us back a lot of the important physics. And now we can use this, now we can proceed to see what the effect is on the Eikonal resummation. This is, of course, a much larger calculation. So the first step is to define the proper ladder diagram. So this is for some arbitrary n exchanges, and we will sum over all possible n in the end. So there are n different gravitons, and they each have their own momentum k. Then on top we have to add all those k's together for momentum conservation, and on the bottom we subtract them. And each of the different propagators is also at their own lm. So the gravitons have the capital Lm and the scalars the small ones. And the ones on the bottom we denote with a bar to keep track of the difference of the bottom and top. And the graviton momenta on the bottom that are subtracted have this pi in them. And this is because we want to allow the gravitons on the bottom to be permuted in any way, and sum over all these permutations in the end to keep them as general result. And this pi allows us to keep track of this. So a couple of definitions in here that are useful are the capital K, which is the sum of all of the momenta up to that point. And then the bar is the same, but on the bottom, so we need the pi in there. And we find the matter propagators, scalar propagators, using a Klein-Gordon propagator that we saw before. There's also the L and the L bar to distinguish them. And the CL of all the M's is a shorthand notation, slightly shorter, for this integral over the YLMs. And then the amplitude is given by this expression. So it's a large combination of terms. So there are a few points of interest. There is this summation over all the possible permutations, which will be important. Then there is overall conservation of momentum. So the total amount of exchanged gravitons, capital Kn, must equal the Q plus that we found before in the tree level. And all of the scalar propagators are put here in a small group. And the rest of the contributions all comes from the vertices. And the question at hand that we want to solve is to do this resummation over all of the partial waves. So we want to resum of the LNM. And at this point, this is simply not possible because the LNMs are present in the scalar propagators. They're present in the coupling of the vertices and the graviton propagator, and they're present in the CL functions. So we need to do some simplification in order to proceed. And this simplification is again the Eikonal approximation that we also used before. So essentially what we will assume is that all of the graviton momenta individually are also small. They're all of the order of Q plus. So we don't just want the total momentum exchange to be small, but we also want the individual exchanges to be small. And in this approximation, the matter propagators simplify. So on the left-hand side, we have the exact contribution, and the simplification is subtle. So working out the square, we get the 2p1.k contribution. There's a p1 squared, but this is on the mass shell. So it removes the m squared, but the mu squared lambda 1 is at a different lambda. So we have to keep this difference. And finally, working out the squared gives a k squared. And this k squared we could neglect by the approximation. So far the approximation only removes the k squared. And now the propagator, whereas it simplified a bit, there is still this problematic mass term. And in the minimal coupling, we ignored this mass term under assumption of large P1. So we just blindly ignored all mass contributions. However, at that point, we didn't have the explicit Q plus solution. And now we can see that Q plus dot P1 is actually of the order of mu squared. So these terms are of equal order, and we definitely cannot remove it just like that. However, we do need some simplification still because the scalar L is in there, so we cannot do the resummation. So the solution that we found is to redefine the loop momenta to not be the natural momentum. Sorry, yes?
Yes, what is the justification of dropping that elsewhere? Because we are integrating over the this loop momentum, right? And there the official equation is from 0 to infinity. Now, could you clarify that justification for dropping this elsewhere?
Yeah, so this is a very good question. And because the full calculation is impossible, it's sadly not possible to compare the orders. The justification, and this has been checked, I believe, in Meson cases, Meson scattering diagrams, is that the contribution from going to the UV is subleading compared to the contribution where the exchange is small. So the key part is that we always have this S that is extremely large. And the assumption is that if this S is large, the leading contribution to the scattering will always come from this regime. And taking K to be any exchange of an order higher will only give subleading contributions. That's the assumption. However, in gravity, we cannot, for once, on the one hand, we cannot easily show this just because the calculation is too difficult. But also, of course, the graviton is not UV complete, so there's also a fundamental issue. So this is a fundamental assumption essentially that we're making, that the fact that this contribution dominates, as it does for other particle physics calculations, also does for the graviton. That's the reasoning.
Yeah, so is there any place that assumption can be violated or this assumption can be wrong?
Do you mean, for example, is there any diagram where this would fail or any?
Right. Like the diagrams that he showed are all like a box diagrams. So if we consider some other kind of topologies, the Feynman diagrams, could it have gone wrong, this assumption?
Yes. So I would definitely say that this can only be done because we are considering exactly these ladder diagrams where it's possible for the scalars to sort of stay on the same momentum and have the gravitons be little. But an arbitrary diagram could have different loops. There could be scalar loops contributing, and then at least there is maybe a different approximation that one can make in the limit of large S, but it's not this one. The K will have to be something completely general, such a diagram. So yeah, for other types, non-ladder diagrams, you would have to do the full integral.
Okay, thank you very much.
Yes, thank you. Yeah, so we want to carefully, in a precise way, see if we can remove the mass term. And the solution that we found was to redefine the loop momenta, so that they're not defined in a natural way to the graviton propagators, but rather to the entirety of the diagram. So we shift them by some small amount that exactly resembles the Q plus, because there's a difference of all of the masses on either the top or the bottom. So effectively, the redefinition of the loop momenta ensures that not just overall, but for each individual graviton, the different mass contributions are exchanged and absorbed into the graviton momentum. So this gives a very natural way of ensuring all of the masses work out. And by doing this redefinition, we find that in the leading order, the mass term can be removed, and we have the desired Eikonal behavior. And there are additional effects of this rescaling, which is that the sum of all of the graviton momenta gains a contribution coming only from the external legs, which we can identify to be exactly Q plus. So this rescaling, redefinition of the graviton momentum trivializes the momentum conservation because it's now automatically included in the parameterization that we've chosen for K. So that's a nice accidental consequence. And finally, we can also apply the small momentum exchange on the vertices. And this turns this huge vertex into just two contributions. One is the contribution coming from the solved part that I showed you before. This is just metrics. So we can subtract and take the limits of large S. And then this is the only remaining contribution, which now only depends on the partial waves of the graviton, but not of the scalars. And then there's a contribution coming from the hard part still. But this contribution we'll see drops out and also only depends on the partial waves of the graviton and not the ones of the matter. So we can combine these three identities, so the rescaling of the momentum and the Eikonal approximation, turning the amplitude into this. So some simplification happened, still a large expression, but more importantly, the matter partial waves, the scalar partial waves, are now only present in these CL functions. The rest of them has been absorbed into the integral. So we can resum over the LMs as we want to do in the first place. So we can resum the partial waves, and this is a lengthy but straightforward calculation. So the trick is to write out all of the CLs back into the integrals and spherical harmonics. Then there are 2n of these integrals. There are 2n minus 2 sums over the harmonics, giving delta functions. So two integrals remain. We find exactly the YIV that we also saw on tree level, the external harmonics, and a product over the remaining harmonics of the gravitons that have not been resummed yet. And because this is a simple product, it's permutation independent, which is a useful observation. So we can just remove the pi's here and instead write it like this. And this permutation invariance finally allows us to rewrite the amplitude into this. So there's the prefactor, there's the two integrals in the YIV similar to tree level. The remaining sum over the graviton harmonics can be grouped together in this way to the power n. And then we have the Eikonal matter propagators. So the first observation is that also in this Eikonal resummation, the graviton harmonics sum up to give exactly the Green's function that we saw before. And the remaining observation is that the sum of the permutations now only affects matter propagators. So we only need to shift our question of what the effect of the permutation is to those. And this is again the combinatorics problem that was done by Levy and Suger. They did things without partial waves, but we've now also integrated out the partial waves. So doing this carefully shows that matter propagators can be put in this product, this factorization of the Eikonal propagators, where the graviton momentum for each graviton is contracted with both the momentum on top for the one and the momentum on the bottom for the other, and then subtracted in a careful way. And now we can use this identity, which follows from doing a contour integration in a complex plane in the limit of small epsilon. And this turns the identification that we had here above into just delta functions. So this is the reason why the Eikonal approximation, this Eikonal form of the propagator is important. It allows us to rewrite this into delta functions, which finally sets the remaining graviton momenta in the integral to 0. And this allows us to write down the full ladder amplitude for the resummed case like this. So we have again the free field theory contribution. There are the integrals and the YIV similar to tree level, but the remaining factor has been put into the exponent with the familiar Green's function. So a nice consequence is that the numerical factors now naturally agree with the ones of the Hooft. There was a previous mismatch in the minimal coupling that we had to interpret differently, but now this all happens naturally. And there is a resemblance between this amplitude and, for example, the celestial Eikonal amplitude, as was derived by de Goya and Zaclariu, who also have an amplitude where there is some integration over the transverse positions, or the orthogonal positions, some basis eigenfunctions, and a complex exponent with a Green's function. So we have some nice resemblance with literature after doing this resummation. And now we can finally ask the question of what happens when we put the particles at some fixed angle. So we do again this resummation of the harmonics. And we find that the S matrix is given by just the complex exponent with the Green's function in the exponent, measuring the difference. Now this Green's function does not have a very nice closed form. It became some Appel hypergeometric function. But if both particles are very close, we can make a nice approximation, which is that the Green's function is proportional to the logarithm of the distance between them, with a -1/2 pi in front. And inserting this approximation into the exponent turns it into this e to the minus I2gs log g. And this precise form of the S matrix has also been found by Cabot and Ortiz in 1992, when doing an Eikonal resummation on flat space without partial waves. So it appears that our resummation works in the sense that we obtain a similar result. So the partial wave resummation accurately captures the effect of the distance between the particles, which is what we hoped to restore. An important difference is that in the calculation of Cabot and Ortiz, they did the calculation on a flat background, which means that they had to insert an infrared regulator for the graviton by hand. However, the mu bar that we have here is related to our effective mass parameter mu coming from the black hole and some numerical constants like the Euler-Mascheroni constant. So the regulator mu bar that we have, we don't need to insert by hand. The black hole functions as a natural regulator. And this is a nice consequence. So finally, we can compare our amplitude with the one of the Hooft, our S matrix. And what we find is that the numerical factors agree. There's a factor 2 in the S, so this matches. But there are still some problems, some mismatches. One is that the integral over the omega bar is outside of the exponent rather than inside, which is a big difference. And we have the presence of this YIV, and there's no trace of any YIV in the Hooft's S matrix. So there is some difference. Upon closer inspection, however, of the S matrices, if we insert single particles in Hooft's S matrix, so there is no summation, and we compare this to our result in the position space, we do find an exact match, including numerical factors and the Green's function. So it appears that somehow we are not capturing multi-particle behavior. And this was on one hand to be expected, of course, because we calculated 2-to-2 diagram. But there has been some long discussion going before this about the interpretation of the spherical harmonics expansion of the scalar phi lm, where the phi lm would be a density of many particles in a single shell. However, as we will see from a Fock space setting, it doesn't work like that. So we need to generalize to the particle. So to summarize, we've resummed the partial wave basis now also in the Eikonal. We found some matches and resemblance with literature, reinforcing the fact that this resummation works. However, we've only managed to capture a single particle interaction. So the next step would be to define a proper Fock space many particle state and scatter those. And this brings us to the final part of the talk, where we generalize this Eikonal to arbitrarily many particles. So the setup that we consider is elastic scattering of n plus m particles, where the n refers to the amount of particles that go into the black hole, and the m the amount of particles that go out, and they will have some gravitational interaction. And to do so, we now first want to properly define the particle states, which is something we didn't do before, but felt necessary at this point. So because we've done all of the transformations in the toolbox paper with the well transformation, the horizon approximation, the metric has become effectively just two-dimensional flat. So the quantization is given by a usual canonical quantization with annihilation and creation operators, the modes, and integration over a single momentum that must be bigger than zero for causality. And then the momentum, we can fix either of the two in the integral, and then the other one is automatically fixed by the on-shell condition, by the mass. And from this canonical quantization, we can extract two possible commutators. Namely, we can put this in the LM formalism, and then we have the canonical commutator with a diagonalization. Or we can write down a canonical commutator in the position basis, where there's also some diagonalization. And now we can use this quantization, these operators, to define the number operators in particle states. So because in the integral we could choose either of the one momentum, we will use this for some smart bookkeeping. So we will define the particles falling into the black hole by their PU being dominant, so that the integration is over PU, and the outgoing we will define by PV being dominant. And this allows us to define two separate number operators for the different particles, where the y is v and x is u. At some point they switched convention. So we have the number operator for the out particles by integrating over all of the y or the v momenta, and for the in, resolve the in momenta. And this allows us to nicely define the n plus m state, where we have some in state, which with a creation of n particles with P1, and creation of m particles with P2. So this creates n plus m particles in total. And this can, again, also be done in the position basis if desired. So graphically, what we consider is now the following picture. We have n particles coming from asymptotic infinity moving into the black hole. We have m particles that go out of the black hole. There's some interaction in the middle, gravitational interaction that we will calculate. And then they proceed on their path, preserving the total m plus m, because the scattering has to be elastic. And so the next step is, what kind of scattering do we want to consider for this process in the middle? What kind of graviton? And generally speaking, there is an extremely large amount of diagrams, because m plus m can be anything. So the calculation will be very hard. However, we have a very specific question, which is that we want to generalize the Eikonal calculation. So we want to assume that there are some large momenta, large Mandelstam S everywhere, and that the impact parameter between the particles is also large enough, so that they basically do not exchange much momentum. So we want a small momentum exchange. So the aim is to draw a diagram that ensures that all of the particles interact only once, because this is an analogy with the classical picture, where they just cross this shockwave once. So this is an heuristic argument to get in touch with the Hooft's picture. And that there's also a small momentum exchange everywhere. So we need an Eikonal interaction. And then the only diagram that immediately follows is to have this sort of grid, where there are n particles and m particles, and they all cross each other exactly once in a grid. But because we want to do this iconally with small momentum exchange, each vertex in here is now actually a complete Eikonal 2-to-2 resummation. So each vertex consists of momentum conservation, conservation of the angles, because it's also a result of the Eikonal, and this complex exponent that we derived in the previous part of the talk. And now the aim is to calculate this amplitude using these definitions. So first we want to parameterize the diagram in a smart way. So we will put it into this more rectangular grid just for readability. And then we can look first at what the contribution is of the vertices. So each vertex will be at a different angle that we must integrate over. However, at the same time, because the vertices are Eikonal, they also conserve the angle. So this all trivially integrates out. And across each of the flow line, we call these straight lines the flow lines. Across each of them, the angle will be conserved. So a particle coming in at some omega 1 will come out at omega 1. The remaining contribution of the vertex then comes from the 2s and the exponent, which we'll simply have to multiply over all of the different vertices, where the Sij is a notation for the center of mass energy between the ith and jth particle. And because we have a product of an exponent, this we can simplify into a sum. Prefactor remains, but the exponent becomes just a sum in there with the Green's function. And this is the entire contribution of the vertices. And now the more important question is what becomes of the contribution of the propagators. So to keep the calculation general, we want to allow for any permutation over the external legs. This is why there is the B notation. So originally we had of the external legs with some P1, P2, and the B1, B2 set is essentially a permuted set of the original one to allow us to keep track of the permutation. And the internal momenta are so far arbitrary and just added on top of the different momenta of the scalar. And along these flow lines, we also make similar definitions where the capital K is the sum of the gravitational momentum up to that point. And the capital Q is the momentum exchange between the permuted B's. So Q is just the permutation of the original momentum exchange. And in this diagram, there are two special lines, which are the R1 and R2, because everywhere we add the gravitational momentum to the scalar, except along these lines, where all of the momentum instead flows back in the other direction, so that the momentum is conserved in total. So the R1 and R2 lines are a trick to do that. And in the end, we want to sum over all R1 and R2 to keep things general. So let's first look at the contribution when we are not on the R1 and R2 flow lines, so of the special ones. Then we don't need to rescale the momentum and to have the mass fixed at this point, because the propagators are all in an angular basis now instead of in an LM basis. Then we can see that the flow lines that are not R1 and R2, they all have B plus K. So the Eikonal propagator, when we write it out, is of this form, with a minus sign due to the metric. So these will have some pole in the negative in the lower half complex plane. However, the flow lines of R1 and R2, they have some B minus K. So when we write out the Eikonal propagator there is a minus K. So the poles there lie in the upper half complex plane. So you can remove all of the ones that are not on the R1 and R2 by a complex integration over the lower half plane. And doing this replaces all of the propagators just by the residue and sets the momentum of that specific scalar leg to 0 everywhere. And then the total contribution of all of the flow lines that are not special becomes just a product of all of the residues. But this product is permutation independent. It's a simple product. So it's equivalent to a direct product of all of the non-permuted momenta. And as mentioned, the internal K are all set to 0. So this is contribution of the ones that are not R1 and R2. Now we want to look at the R1 and R2 ones. The R1 and R2 flow lines are all given by this. So there's a huge sum end product of propagators that are all iconalized, and then added together before taking a reciprocal. And there are there are a few important things in this expression, which are all of the different sums over the permutations. So there are momenta before the R2 and after, and we want to allow any permutation before, which we call the pi2, and the after, which we call the bar pi2, the complement. And then we have to sum over all of these different permutations. We have to sum over all of the different ways that momentum can be, the original momenta can be distributed along the B's, and we have to sum over all of the possible values of R. So there are a lot of combinatorics that must be resummed. And a part of the combinatorics that had to be resummed has been done by Levy and Sucher. And a part was new, so we had to find some new identity. And we could use this in combination with this earlier Eikonal identity to show that the special flow lines reduce to just this product. Where now the Q are the original momentum conservations. The Q are the original momentum exchanges of the external particles. So what we see is that the R1 and R2 flow lines actually reduce to momentum conservation along each flow line. So momentum conservation for each particle. And this is what was sort of desired within the Eikonal formulation, where all of the particles had to exchange very little momentum. And this is achieved by carefully doing these combinatorics again. So finally, we can combine this to have this full amplitude given by this. So we see the exponent that we saw before coming from the vertices. And then there are the products of the momentum conservation, the conservation of the angles that we mentioned, and not other factors that come from the contour integration. Similar. Now, in this expression, we can recognize the free field contribution using the commutator. So this is something that we only noticed at this stage, but we can find the free field contribution explicitly. So we can use this commutator to write down the S matrix in terms of free field one, and again, it becomes a pure exponent. So this is very nice because we wanted to generalize the Eikonal, and the Eikonal always gives pure exponent S matrices. And now we've also found this for the arbitrary particle case, which at least to my knowledge has not been done before. In this process, we also found a free field theory result, which was added in retrospect to the 2 to 2 calculations, which you've seen in the previous parts. And as mentioned, this S matrix gives a direct generalization of the Eikonal to an arbitrary amount of particles, so that effectively we have written down the most general possible Eikonal amplitude that one can make. There are no more generalizations that can be done. So finally, to compare this with the S matrix of the Hooft, we can write out the sums in the exponent, the momenta in there, with a factor 2 coming from the S. And we can artificially define distributions coming from the eigenvalues of the external particles. So all of the external particles are at some position and angle. And we can put this in a distribution And then finally, the S matrix becomes this exponent, which is exactly the result that the Hooft has. So we can finally conclude that by doing this whole many particle Eikonal calculation, we fully recovered the Hooft result. And the quantum mechanical densities that he defines directly correspond to the distributions that we can artificially define, artificially construct from the eigenvalues of our Fock space particle states. And while doing so, we also found a complete generalization for the Eikonal to an arbitrary amount of particles. And it's an exact match, which I already mentioned. So yeah, to conclude, what we have seen is that the Hooft had derived a semi-classical S matrix using quantum mechanics and the shockwave, which was given by this exponent. And we have now finally managed to completely generalize this in field theory to find an agreement in the elastic M plus M scattering. And this elastic M plus M scattering is also, to our knowledge, something that hasn't been derived before. And we also found some additional resemblance with literature. So with the log of the B and the Schlesinger-Eikonal amplitude in the 2-to-2 resummation. And some shortcomings of this specific diagram is that we have no proof why this specific diagram would be the leading contribution. Heuristically, we can argue that this is only valid in very specific conditions, which is if all of the particles are sufficiently far away separated so that they exchange little momentum. But all of the individual Eikonal scatterings would also need to happen in a different time frame, because otherwise we can expect the gravitons to start mixing. So this is a very specific result. However, we also didn't have a strong desire to prove that this is a leading result, because at this point we only want to find the corresponding diagram that retrieves the Hooft result. And the fact that it does that also gives some reinforcement that this diagram does make sense, at least in some way, because we find the correct agreement. And finally, this whole scattering is defined only near the horizon, on the horizon, and it would be nice to properly bridge this at some point to asymptotic infinity. Some additional results that we didn't mention is that we've defined the positions field theory now also in the angular position space. An extension to SQED has been done to scalar QED with in collaboration with Fabiano. And previously, we've also already calculated one inelastic scattering of scalars, which I will not go further into now. And as mentioned, there are many more future possibilities. We hope, heuristically speaking, to be able to calculate the near horizon processes beyond the elastics, so the EMRIs, using radiative diagrams. And we hope to use the field theory to write down soft theorems and their corresponding symmetries, and possibly extend this to quantum electrodynamics to include fermions. So as a takeaway, the most important conclusion of this talk is that we've managed to develop a field theoretical method to obtain a Hooft S matrix, and previous mismatches have now all been corrected by doing the correct full partial wave resummation and including an arbitrary amount of particles. And while doing this, while developing all of these methods, we've also found the most general possible Eikonal calculation, because this has previously only been done for 2-to-2 particles, and we now have generalized this using this grid diagram to an arbitrary amount. And finally, hopefully in the near future, we've developed a framework that can be used to calculate radiative processes. And in particular, we can hopefully describe the gravitational radiation of EMRIs. And thank you for your attention.
Yeah, let's thank Nico for a wonderful talk. If you have any questions, please go ahead and ask.
Can I ask a question, sir?
Yes.
Yes.
Yeah. So, could you study a similar problem for say a EDS planar black brane? Because over there, the all of this spherical YLM business will simplify quite a bit, right? Because you could just work with planar waves.
Okay, so I don't know specifically how things would simplify on ADS, or at least on ADS Black Brain. We have considered generalizing the calculation to include, to an ADS space in order to make more connections to literature there. But so far we haven't had the time, and I'll be honest that I'm not sure if I will have the time for this in the future anymore. But it would definitely, yes, be a very nice addition to do this also on ADS. And you say that on ADS planar brain specifically, the harmonics would simplify?
Yeah, because the plane waves are much simpler to work with than spherical partial
Right.
waves, right?
Yes. It could greatly simplify the problem, at least on the technical side. That's definitely true. This would be a very nice addition. Yeah. Thanks. That's a good comment.
More questions? No, I didn't see any more questions. So if there are no more questions, let's thank Nico once again.
Yes,
Yeah,
thank you.
thanks a lot. Yeah, thanks a lot.
Thanks for having me.
Bye-bye.
All right, bye-bye.